Hey guys, here is the video for higher derivatives with sound. Hi. Higher derivatives, that is. So the notation for this, you'll see y double prime or maybe f double prime. Those are probably the most common. But remember, we did have dy dx for the derivative, so it could be d squared y over dx squared. Would also represent the second derivative. Suppose f of x equals x times cosine x, and they want us to find f double prime of x. Well, we got to find f prime of x first. So here we go, a little bit of a product rule. Clean it up just a little bit. And basically double dip. So it's almost as if this is the new original and you're just looking for the first derivative. So most of the time, this is pretty much what you'll end up doing. Just take the first derivative, clean it up so that it's easy to take a second derivative, and then bring it home. So this did require an extra product rule with a little bit of cleaning up you could do. And there you go. There's your first second derivative. See what I did there? See that? See that? Did you hear that? Hit rewind if you missed it. There it is. Okay. All right. Yep. Any questions? Nope. Good. Thanks. Cool. Let's move on. All right. Suppose you've got the position function for a particle. All right. So you got t cubed minus 6t squared plus 9t. That's the position. And they're going to ask us something about acceleration. So we talked about this in class. Right? The first derivative for a position function would be velocity. And then the rate at which the velocity is changing with respect to time would be the acceleration. So first things first, let's find velocity. So that's s prime or f prime of t, which is v of t. So that's 3t squared minus 12t plus 9. And our second derivative would be f double prime, which would be v prime, which is the same as acceleration, so a of t. So this one looks like it's 6t minus 12. If they ask us for 4 seconds, well, just plug in the 4 just like you would if it was what's the velocity after 4 seconds. And the units would be meters per second squared, because if velocity is meters per second, well, this is meters per second. So that's meters per second squared. And there's your acceleration. Yep, I think I said that a minute ago. So it's the rate at which the velocity is changing with respect to time. Smiley face. All right, so one of the things that's helpful is to actually look at a graph. And this is where it can get a little confusing because you sometimes forget, by the way, that's not let's graph them all. Let's graph them all. Sometimes the graphs can get confusing because you kind of forget which ones you're looking at. So what I do in the calculator is I'll change the lines that it uses. So like either regular line or thick line or dashed line. Sometimes that helps me to see which one's which. Eventually, you'll probably end up looking at the velocity and acceleration together without the position necessarily. But so here, let's say it might not be a bad idea if you put this in your calculator too, just to get used to what it looks like and how you can manipulate it and sort of focus your eyes in on what you want to focus your eyes in on. In fact, I'm not sure the dash line really did a good job on this one anyway. Works better if you change the resolution or maybe if it's a curve. I'm trying to remember if this one actually did it or not. We'll see. We'll see together. It'll be fun. All right, so there's the original. That's the position function. There's my velocity. I made that thick. And yeah, it almost looks still. There's a slight hint of jaggedness to it, but it almost looks like the original. The only reason why this one's easy is because you know it's linear. All right, so one of the questions you could get asked is, when is the particle speeding up? And the particle speeds up when the velocity and acceleration are basically doing the same thing. So they're either both positive or both negative. All right, my writing will catch up with us in a second. So basically you're looking for, how do I word this without showing something else? when the velocity and acceleration are acting together, like your velocity is positive and your acceleration is positive, so it's moving in the positive direction more positively. Does that make sense? If it's moving in the negative direction more negatively, it's still speeding up. It's just speeding up in the negative direction. So I'm pointing here to where the velocity is above the axis versus below. And I'm looking for when the velocity and acceleration are literally on the same side of the x-axis. If they're on the same side of the x-axis, that means they're either both above or both below. I know the object's speeding up. So again, if it's moving in the positive direction faster and faster, then it's called speeding up. If it's moving in the negative direction more negatively, well, then it's still speeding up. It's just speeding up backwards. You can accelerate in reverse, right? So that's the idea for speeding up. So I did it on the calculator. Sorry, I went a little quick there. So I did it on the calculator. I just looked. I knew where the points were. But algebraically, just check it. Make your number line. Figure out when the velocity is positive. And then use that to determine, half of the problem, really. So we've done this before when we did snake graphs. So if you're looking at your graphing calculator still, or you rewind it, you can see the velocity graph is above the x-axis between 0 and 1 and after 3. And that's half the problem. Now, the object is not speeding up just when velocity is positive. That just means it's moving to the right. It could be moving to the right and slowing down. Right? If you're driving a car and you hit on the brakes and you start slowing down, yeah, you're moving in the positive direction, but you're slowing down. So even though your velocity is positive, your acceleration is negative in those cases. So let's check the acceleration function, which I think was just the basic, like 16 minus 12 or something. 60, yep. So solve for t, you get t equals 2. There's your breaking point, or your breaking time, really. So 0, 2, do the same number line, but do it for acceleration. And what you're looking for is when is the velocity and the acceleration doing the same thing. Might be hard to see it in this picture right now as is, but if you line them up together, it'll be easier. Okay, I think I'd do the calculator first before I put them together. I can't remember. Wait for it. I think I summarize it first. So the particle's speeding up when both are the same sign, right? Yep. So it looks like what? Between 1 and 2, they're both negative, and then after 3, they're both positive. That's what it looks like from the number lines. So that's what I meant by both, velocity and acceleration. That's not like a coordinate. This is where I read it. Yeah, see, I'm pointing to positive between 0 and 1, negative, then positive, right? And then you can see it on the graph. Here you go. See how they're both below the x-axis between 0 and 1, or between 1 and 2, I mean, and then they're both above the x-axis after 3. And here you go. Here's your summary. I think that honestly, I think the easiest way, well, besides the calculator, one of the easiest ways is just line up the number lines right on top of each other almost, and you can just see where they're the same. And I think I do that in a second. So if you already saw this, you can fast forward probably a little bit. Wait, get to the number line and you'll see. Here it is. Combine the number lines. I feel like a sports commentator or something. Miller grabs the pen and starts writing stuff on paper. Now he grabs another piece of paper. I'm on the edge of my seat. Actually, I am, because I'm just kind of leaning forward. But all right, so there's the velocity line. Same. I'm just copying it. In retrospect, I should have done this one in red, because I did do the velocity originally in red. But I did them differently, so at least you can still see. And there's the acceleration. And here's where you really get to see it. Just look at both of them. Look how they overlap each other. Right? In the beginning, 0 to 1, velocity is positive, but acceleration is negative. That's slowing down. So between 1 and 2, they're both negative. That's why I shade that in. And then after 3, they're both positive. So they're both speeding up intervals. One might be speeding up in the negative direction, but that's okay. It's still speeding up. They have the same sign. That's what it means to speed up. Then I think I talk about slowing down now too. So basically, slowing down is exactly the opposite of everything I just said. So it's when they act against each other. Think of, this is the easiest one. Literally think of being in a car, driving 50 miles an hour constantly, then starting to hit on the brakes a little bit to slow down. Your velocity is positive, your acceleration is negative, you are slowing down. That's it. It's that simple. Okay? Maybe fighting each other is a bit strong, but that's the idea. They're going against each other. So between 0 and 1, again, velocity is positive, acceleration is negative. Between 2 and 3, velocity was negative, acceleration was positive. And that's it for that. Next. Suppose, this is the one Nate brought up the other day, okay? I think when I had hinted at, I forgot if I had even said higher derivatives, but he came up with, if you take the fourth derivative, don't you end up back where you start? And he was absolutely right, and this is exactly what I'm showing here. So some ridiculous questions ask you to take ridiculous amounts of derivatives that really have no context or application in that form. Now, it doesn't mean we won't take more derivatives than 2 or 3, but in a situation like this, they're just doing it for the sake of seeing the pattern. So every fourth time you end up back where you started, wherever you happen to start. It's a very cyclical derivative. Okay? So the 27th is basically the same as the third, right? If you go through 6 times 4, right, you just back at the beginning 6 more times, just back at the beginning, then you just take the third derivative, which is the remainder, you end up at negative cosine. So the 27th derivative of sine is negative cosine by using the pattern. That's just, it's just sort of an oddball example, but that's it. Oh, sorry, I messed up the video there. There you go. Sorry about that. Again. All right, I think this is our last example, if I remember correctly. So suppose you have something like this. X to the fourth plus y to the fourth equals 16. Wait for it. There it is. And they want y double prime. All right, so this is totally implicit, right? You see the y is not all by itself, so we do our basic implicit. Solve for y prime like we did in the previous section. And then it gets interesting. Stuff gets real in about 1 minute. I'm just cleaning it up. You always want to clean these up. I know I've said before, don't worry about simplifying. In a situation like this, you always want to simplify. Otherwise, it makes the second derivative even more complicated. So our second derivative is going to require a quotient rule here. I'm going to leave the negative in front just because I think it's easier to do it that way. And then, SpaghettiOs. We have a y prime in our y double prime. We can't have that. Okay? The thing is, we know what y prime is because we just solved for it. Y prime is negative x cubed over y cubed. So substitute that in. Then everything's in terms of x and y. So here's y double prime. And this will pretty much get you 95% of the credit if you get to this step right here. If this is on your paper, you will get pretty much everything. You might lose a half a point, maybe 1 at the most if it's a lot, if it's worth a lot. But this can be simplified and probably should because it really does break down nicely. So in a second you'll see I'll multiply through, and those of you that have watched the video already, you realize that I did not make it positive by accident, right? Watch this. So the negative in front is the same, 3x squared y cubed, and then right here I have a negative times a negative. But I wasn't focused on that. I was focused on the x's and y's, and I forgot about the other negative. So in a minute, I'll fix it. So just sort of simplifying that a little bit. Getting a common denominator in the numerator. That's why you see I'll end up writing 3x squared y to the fourth. I'm multiplying by y over y for the term on the left there. So I can combine them. And that's the same as bringing the y all the way down into the denominator, by the way, which is what we'll do next. As soon as I get enough room on the page. And there we go. So negative 3x squared y to the fourth minus 3x to the sixth. I'm not going to change that over y to the seventh. And now I'm going to factor out a negative 3x squared. And right here, this is the funny part. Watch this. See how I wrote plus? There's clearly a minus there. But I knew it was supposed to be plus because I've done this problem like a zillion times. And I'm like, wait a second. And then because I kept using different pages, I couldn't see it right away. And then I remembered. I was like, oh yeah, I think I remember now. And then negative times negative is positive. Yay. Oops. My B. All right, so it's an easy fix though, thank goodness. So plus plus, and I don't know why I crossed that out. I thought I had written it wrong originally. That should just be the same as what it was going to be originally when I first wrote it. I guess that's what originally means. But there you go. And here's how you know you did it right. This always happens on these. You'll end up back at the original somehow, some way. So look for that, and then just substitute that back in and clean it up. Holy cow, no way. Way. So bring that down, whatever it is. And again, this isn't the end of the world if you miss this. It's just algebra at this point, right? We've done the calculus like an hour and a half ago. So put in the 16. I think that ends up being negative, 48 x squared over y to the 7th, and then that's as far as you can go. So the most important thing is when you're doing y double prime, make sure that y prime is not in the answer. Boom. There it is. That just happened. All right. Have a good night. Let me know if you have any questions.